So let's continue from where we left off last time, which is the second lab titled Expressions. And what we did last time is we looked at exercise 1, and we partially solved that exercise. And then there's this exercise 2, which is an old exam with problems that resemble the problems that you'll be given on the upcoming exam as well. And so you should, I recommend you get started on these problems and try to figure them out. Don't do it the night before the exam. You should do it today, if not yesterday, because you want to start practicing these. And they may be trivial for some of you, but not many of you. For most of you, these problems are going to take some effort, and you'll need to develop a new thinking style. You have to think more about algorithms and how algorithms are expressed using computer notation. It's not something that most of you have done or have done very much of. So don't underestimate the amount of time you need to put into this to prepare for the exam. Start preparing early. And I can talk about the solution to these problems before the exam. But it won't be very meaningful unless you've made an effort first to solve them on your own. And then when I explain how to do them, hopefully that will help you grasp the technique and the thinking style that you need to have to get these problems solved. All right, so that's exercise 2. Then exercise 3 is to write a program that generates random numbers, 100 random numbers, 100 random integers. So the C++ standard library contains a pseudo-random number generator. That means it looks like a random number generator, but it's not. It has some pattern in it, so it has some predictability in it. So that's why they call it pseudo-random number generator. And there's a function called rand, and when you call that function, it returns a random number. To use this function rand in your programs, you need to include this header, C standard library, C standard lib. And the function rand is relative. How the function rand performs is relative to a seed value. So for a given seed, like 3, the rand function will produce exactly the same sequence of numbers every time you call it. So to get a different sequence of pseudo random numbers, you need to change the seed value. So the way to change the seed value is to call another function called srand, or seed random number generator. S is for seed. And you pass in an integer. That's just an example there. It's some video games, they have like a seed, right? Like I think Minecraft. Does Minecraft have a seed? So you generate a world using a seed. If you use the same seed, you get the same world. Is that right? But that's the same thing here. So that in the Minecraft and the similar games do use a pseudo-random number generation system. And with the same seed value, it will generate exactly the same world. So you change the seed value to get a different, in this case, a sequence of pseudo-random numbers. So this is called once in the beginning of your program. You don't call this over and over again. Just call it once in the beginning. And then whenever you call rand, it'll produce a random integer. And you can look at that. And let's do that, actually. Oh, and here's a technique. This random seed, rather than hard coding a value in there like 719, because 719, each time you want to get a different output from your program, you'll have to, recode the program. To avoid that, what you can do is use a different value as a seed, something that changes from time to time as you run the program. And this function here, time, does that. It returns a number of seconds that have transpired since some epoch. Typically, they use 1970. So the first second of 1970, Greenwich Mean Time, that how many seconds have elapsed since then? Maybe they don't. Maybe they use local time. Maybe they don't use Greenwich Mean Time. I'm not sure. And not all systems use 1970, but the Unix-based systems do. Maybe Windows does as well. I'm just not sure about that. But that was a typical time epoch that was used. And so you can, in your code, you can say you call this time function. It returns the number of seconds since 1970. Say, let's take that, and then it takes arguments. So the time function has different behaviors. And sometimes it'll return a number of, hours. I actually don't know how the time function works in detail. I just know that when you pass in a 0, it'll return a number of seconds since some fixed epoch, which I think is 1970 on most systems. It doesn't really matter what the epoch is. So as long as you get something that varies each time you run the program, so you get different behavior, if that's what you want your program to do, which you typically do if you're using a random number generator. So what we want to do is write a loop that generates 100 random numbers. Actually, this is not right. List item entries. This is from an old problem, actually, when the numbers appear inside of a web page. So I didn't modify that text correctly there, so that you can sort of ignore that. Generate a list of 100 random numbers. So when you write the program and compile it, you get this executable. So when you run the executable, it will just display 100 random numbers. And maybe we want to store that in a file. So you can use this redirection operator and say, oh, instead of writing to the display, write to this file. So now when you run the program, you don't see any output. But if you open numbers.txt, you'll see the 100 random numbers in there. So this tells you how to change. This lets you reassign standard output. So the standard output by default is a console. And here, with this notation here, we're changing the standard output from the console to a file named numbers.txt. And we can open that file in a text editor, take a look at the numbers. So that's what we're going to do. Let's go ahead and do that. So I'm working in a folder called 201. I've got a subfolder called Lab 2. And there I have some problems that we worked on last time. And I'm just going to start this screen program, make it easier for me. And I'm going to copy ex1.cpp to ex3.cpp. That's what it is, 3, right? Exercise 3. So I'm using this copy command, and I'm going to copy that. This is how you do it at the console. And you can do it other ways, depending on your system. And just to verify that, oh yes, there it is. ex3.cpp is created. I'm going to use VI. You can use Nano or gedit or WordPad, Notepad, anything else. It's okay. This is called a text editor. You want to modify. These files have what's called character data. They don't have numeric data in it. Well, I mean, it is numeric data, but the numbers represent characters. So these files contain pure characters. There's no, for instance, like if you have a JPEG file, there's no character data in there. There may be a little bit embedded in there, but mainly it's just numeric representations that represent color values. So the data inside the JPEG file represents color values. The data inside of text files represent characters. It's called character files. So you use something called a text editor to view and modify character files, files of character data. So VI is an very old-fashioned system that provides that capability. So this is the old problem, or this is not what we want to do. So we're just going to get rid of this. I don't think we need this CMath. We'll need IO stream because I want to do things like this. This endl and the cout, as well as these operators, I believe, are defined in IO stream. So we need that include IO stream to use that. But we don't need this CMath. All right, that's how I start a program. I just want to make sure I can build that. And I recommend that you do this as well. There it is. It says OK. All right. Now we need to generate a list of 100 random integers. Let's break it down into steps. And actually, you can solve this problem in so many different ways. And I'm just going to whatever comes into my head, I'm just going to pick the thing. And I just had an idea in my head. That, I get it. The first thing I'm going to do, I'm going to figure out how to write a loop that prints 100 integers. I'm not going to worry about the randomness. I'll just print the number 3, so 100 times. And then later I'll figure out how to replace the 3 with a random number, okay? It's just the idea that came to my head. Because it's hard to visualize the entire solution all at once. You have to have it in the back of your mind, of course. But to write the entire solution out at once is good if you could do that. And it's not the technique that I tend to use, though, because it just doesn't work for me. But it's up to you how you solve problems. So I'm going to show you a technique that I use called incremental development. And in incremental development, you create these runnable prototypes, a sequence of runnable prototypes. They become increasingly more complicated and closer and closer to the final solution. And the final prototype is your final solution to the problem. So you'll see a step of runnable programs that getting closer and closer to the final solution. All right, so we need to have a loop. We need to do something 100 times. I don't think I talked about this yet, right? A loop. So I want to do something 100 times. So I want to print, like I said before, I want to print the number 3 100 times. This is what I want. Do the following 100 times. I'm just going to indent that to show that that's something that's going to be like a substatement. It's going to be repeated over and over again. So that's what I do. This is inside. This is going to be what's called a loop. It's this this shell, this container, that's going to execute its contents repeatedly, well, 100 times in this case. So this, you can think of this line here as being contained within the loop structure. And this loop, of course, is contained within the main function. So you see how the indentation works? That's why this is indented, to show it's within main. And this is indented relative to the loop, to show that it's within the loop, within the body of the loop. All right, so how do we write the loop? We know how to do this. And how do we do the loop? And there's, let's see, let me do it I'm going to do it 2 ways. We're going to have this we're going to declare an integer I. So declare an integer I, set it to 0. And then let's, I'm going to change that a little bit. I'm going to set it to 1 there, okay? Yeah, I have never presented this topic like this. It's always fresh, always. So, so we declare this I, set it to 1, and we're going to use that as a control variable. This is going to be used to control the execution of a loop. And the loop looks like this. We do while some condition. While some condition is true, while this condition is true, we're going to do these statements that are inside the braces. That's it. That's the basis. While some expression evaluates to true. While the expression evaluates to true, do this. And you could do other things. You can have many lines in there. So you could have it, let's do it, just to show that, I'll do this. I'll put 2 lines in there, just to give it more generality. See, there's 2 lines that are executed. I didn't put the printing of the 3, the printing of the new line character. I spread them out into 2 steps now, instead of trying to put it in 1. So this is called the body of the loop, and we want to repeat this. We want to continue repeating that as long as some expression evaluates to true. So we put the expression in here. We're going to say while I is less than or equal to 100. We're going to do this. Now we start by initializing I to 1. So when the system evaluates the loop condition, the loop condition is true because I is 1 and 1 is less than or equal to 100. So we print 3 and then we print a new line. And then we go back and reevaluate the loop condition. Well, I hasn't changed. So we're going to keep doing the loop over and over again. This is called an infinite loop. So this is a bug. If you're using software and it locks up, could be probably an infinite loop, something that's broken, and or it's deadlocked. So this is something, that's a bug, right? So this program will never terminate. So what we want to do is we want to increment I. Each time execute those commands to print 3, to print the new line. As soon as we do that job, we're going to increment I, because I is our counter. It counts the number of times we ran the body of the loop. So eventually, the loop condition becomes false. And when the loop condition becomes false, then execution continues after the loop expression. So maybe I'll just say, like, done. Maybe I'll make it a sentence. Very simple sentence. This brace here, and all the characters before it, up to that W, is a single statement. It's a while statement. It's a complex statement. It has substatements in it. Nevertheless, it's still a single statement. And when the program runs, 3 statements are executed. This statement executes once. This statement executes once. The substatements execute 100 times. But the overarching statement itself only runs once. And the third statement runs once. So you do the first statement, the second statement, third. So it's always sequential, see? Well, unless you get a loop in there. And then and this while loop is one statement. And it causes a block of substatements here, these 3 substatements, causes a block of these 3 substatements to re-execute some number of times. So this should do it. I believe that should do it. Let's see if that works. We have to compile. There it is. This says done down there, right? Now, it's hard to see that there's 103, so just for testing, let's make it easier on ourselves. And just for the time being, let's just print 5, because 100 is too many to deal with in the beginning. Let's check that we get 5. Now we need to recompile because we changed the source code. And then we'll run the program. Those are 5 3s, and then followed by done. So that's called a while loop. There's another loop that you need to learn in this course. It's called a for loop. And I'm going to show you what a for loop looks like. And the for loop, I'm going to comment these out. I'm going to take this comment out too. These 3 lines are going to be replaced by the following line. Okay. What I've done here, I commented out, see the slash slash? That says that the compiler, that's an instruction to the compiler to ignore all the characters following the slash slash. And we call that a comment. And what I've done here is I commented out, that's the verb that you use. I've commented out 3 lines. Int I equals 1, while I less than or equal to 5, and plus plus I. I've commented out those lines, and I've shown you their equivalent, which is this one line right here. So look at this. Look at these 3 lines. This line here initializes I. This line here tests the loop condition. And this line here is like an end of loop operation that modifies something related to the loop condition. That's exactly these 3 spaces. See this? There's a semicolon there and a semicolon there. There are 3 components of the for loop, and they exactly correspond to these 3 pieces of code that I've commented out. And the first component is called initialization. It only runs once. When execution arrives at the for loop, the initialization statement runs. That's int I equals 1. That runs only once. It's not repeated. So rather than declaring it outside the loop, we declare it in this for, using this for syntax. And then the second component, or the second, it's an expression actually, it's not a statement. The second component of this for loop is an expression. That is the loop condition. That loop condition, each time, just prior to executing the substatements, the loop condition is checked. If the loop condition is false, the substatements are not executed. Execution continues after the loop. But if the loop condition is true, then we do the substatements. After we do the substatements, then we execute the 3rd section of the for loop, which is, in our case, to increment I, the counter I. That affects, ultimately, will result in our loop condition becoming false. That's when we exit the loop. So this is the equivalent of expression. And now I'm going to get rid of this. So you see it without, see, it's more compact. So this particular problem, this would be the standard solution. A programmer wouldn't use a while loop because we know exactly how many times the loop runs. 5 or 100. And that's it. And it's simple. It's a simple loop that we just want to repeat something 5 times. So that's normally handled with a for loop because it can be expressed very compactly. We don't have to have that separate variable I declared. We don't have to have the increment of the counter at the bottom of the loop. Those things are easy to forget. So we just use this for loop. Now, when the loop is more complicated, and in particular when the initial condition is complex, and there's no simple end of loop operation like incrementing I, and when the loop condition is complicated, the loop initialization is complex, and when the loop condition is complicated, then we tend to use a while loop. But for simple loops, for instance, a loop where you know exactly how many times you need to repeat something, you'll use a for syntax. Although both loops are equivalent, you can always translate from a for loop to a while loop and the other direction as well. So they're essentially equivalent. Just a matter of readability. You have to decide what is easier for you to read and understand. Let's check this. We don't want to work too much without testing, so let's test that. Looks like 100. Oh, I'm going to put that at 5. There it is. Now there's one more thing I want to tell you about with loops. That computers on the hardware level, they're not like humans. When humans count things, they start at 1. But in hardware, when the computer counts in hardware, it starts at 0. So when I count the people in this class, I go 1, 2, 3, like that. When the computer counts people in this class, it goes 0, 1, 2. Oh, that's 3 people. See how? That's how you think. A human does this. 1, 2, 3. 3 people. But the computer does it like this. 0, 1, 2. Ah, 3 people. You see that? So that is here I coded this loop like a person thinks. Starting the count at 1 and ending at the desired number of repetitions. But this is, you almost never see it this way. Because programmers, listen, I think it's maybe related to tradition, because in the old days, you didn't have high-level languages, like you didn't have C++, you had machine instructions, and then you had assembly language, and then you got Fortran, but it's very close to, you're always thinking about assembly language and the processor and registers and so, historically, you had to work very close to the hardware. But these days, you don't. Although, it helps if you do, of course. And many people have to work at the hardware level. But typically, when you're programming, you don't have to be so close to the hardware anymore. So you're working what's called a higher level language. A higher level language lets you formulate these expressions that result in many machine instructions. When you work in a lower level language, your expressions translate to fewer machine instructions. At the lowest level, like assembly language, 1 expression, 1 machine instruction. So anyway, the thing is that when you're working near the hardware, and that has been a tradition going back in time, you start counting at 0. And that sort of pattern is continued on today. So what do we do? If we start at counting from 0, then we're going to initialize I to 0. And we want to exit the loop when this is how they do it. You could do it like this. You could do it like that. That'll work. That'll run exactly 5 times. 0, watch my fingers. 0, 1, 2, 3, 4. That was 5 times, right? But start at 0. But that's not how people write it. You can write it this way. They write it like this. This is the standard expression that you see. That's the common expression. This is the loop that runs exactly 5 times. You initialize your counter at 0, and your loop expression is that the counter is strictly less than the number of repetitions you want to achieve. As soon as your counter hits the number of repetitions you want, which is 5 here, then you cease executing the loop. So this gets a little complicated. So you have to think about this and digest this. And you start at 0, and then you do this, and then let's walk through. I want to show you how to walk through the code here. Let me make a little note here. So I is going to be, I'm going to do it like this. I is 0. Let's do this. No, we're going to store what's in I here. All right, so we're coming into the program. Now we're going to execute this for loop. So we declare an I, initialize it to 0. So that's the first thing we do. So I'm going to show you what happens in sequence now. So I is 0. And then after the initialization is done, then we evaluate the loop condition, because we don't want to run the body of the loop until we check the loop condition first. That's how it works. So the loop condition is I less than 5. So 0 is less than 5. That's true. The loop condition is true. Therefore, we're going to print the 3, print the new line, and then we hit the bottom of the loop. So, oh, okay, what do we do now? Well, we do the end of loop operation. And that is to increment I. That's the third section. This is the thing you do when you hit the bottom of the loop, when you execute the body of the loop. So plus I means to increment, to increase I by 1. So I is 0, so we increase it by 1. That means it becomes 1. Now, after we do this end of loop operation, then we don't initialize again. We only do that once. We evaluate the loop condition to see if we want to continue the loop. So I is 1. It's strictly less than 5, so the loop condition is true. That means we'll print 3, print the new line. We're at the bottom of the loop. That means we increment I again. I becomes 2. Now we evaluate the loop condition. 2 is less than 5. Print 3, print a new line. End of loop, increment I is 3. 3 is less than 5. Print 3, print new line. We're at the bottom, increment I is 4. Now we got to slow up here, so we got to think carefully. 4 is strictly less than 5, that's true. Print 3, print new line. Increment I, I'm going to the slow motion now. Increment I, 5. Check the loop condition, 5 strictly less than 5. That is a false statement. That expression evaluates to false. 5 is not strictly less than 5. It's less than or equal to 5, but it's not strictly less than 5. So now the loop condition is false. And the loop condition is false means we're done with the loop, the entire loop. And the loop ran once. I mean, the substatements ran 5 times. But the entire loop expression itself was considered to have been completed. It was done once. If you call main 5 times, of course, then you're going to do the loop 5 times. So when we finish this, then we print done, and then we're at the end of main. And main is a function, and I'm just going to give you a little bit of advanced material here, although it's coming up pretty soon, the chapter on functions. That functions need to return a value. So main returns an integer. And so you have this return statement. It says, get out of here. When you get out of here, give the calling code. So all functions are called from somewhere else. And that's called the caller. And so when main finishes, or any function finishes, you need to pass a value to the caller. And main returns an integer that's given here. This is the data type of the return value of main. When main completes, it returns this value to the calling code. And so we use this return expression to say what value to return. But in main, this is optional. So typically, you'll see that because there's an implied return of 0. And when the compiler compiles main, it'll insert return 0 for you. But with other functions, it won't compile. It might. With some kind of default return value, which would be 0. So that's it. Now, we have a loop that we can run 100 times. We're going to leave it at 5 for now, because 100 is too many to look at. But before we submit our work, we'll change the 5 to 100. Now what we want to do is get random numbers here. Well, look, here's another idea. Why don't I just output the I? Look at that. Let's just see how that works, just to play around with it. See, 0, 1, 2, 3, 4. There's 5 numbers. So here I'm putting an integer value. And what we want to do is output a random number. So we call this random function. And that random function, that's a function. Because it's talking about main returns an integer. Random returns an integer too. Now we're the caller. We call rand. A rand looks like it. Rand is a function that looks like this. It has a definition just like that. And it has a return something at the bottom. So we're the caller, we're calling rand. We're letting rand do its thing. We don't know what's going on the inside of rand, but whatever it is, when it gets to the end, it returns an integer to us. And so this expression here evaluates to an integer, and that's what we send to the output stream. There it is. Let me do that up here. Watch this. 5 pseudo-random numbers. What happens if I run it again? Can anyone remember what I said?
It's going to give you the same values.
Huh?
It's going to give you the same values.
Exactly. Very good. It's going to give us exactly the same values because we're using the same seed. I don't know what the seed is. It's some default value. Other languages, I think, are auto seeding. So you get different values for random numbers. Like in JavaScript, which I've been using a lot recently, you don't have to seed the random number generator. And you'll always get a different, you usually get a different sequence of random numbers because it's like auto seeding. All right, so now let's change that. Let's pass in a seed value, srand, that's the function. A 719. I'm not going to use the same number. I'm going to use 44. There we go. Now, I don't know if that's, oh yeah, it was a C standard lib, right? Well, we have to include that. C standard lib. You know what? I think it's compiler dependent. This rand function, I think on Windows you need C standard lib to use rand. Maybe in the labs you need C standard lib, but on my compiler, I can use rand without that header. So there's some differences between compilers. So for the code to be portable, you'd want to use this in here, but this I believe has the time function in it. So I don't think I can. Let me leave this commented out, and I'm going to go as long as I can until it breaks, and then I'll uncomment it. And let's see if it works. Also, I want to get rid of this done. That's extra stuff that we don't need to look at. It's not important to what we're working on right now. Let's see if this compiles. That does compile. Now let's run it. If we run it again, it's going to use the same seed. So you get the same sequence. All right. The seed is 44. But if we change 44 to 45, and then run it, we should get something different. It's pretty close. No, it's not pretty close to the same, but it is different, right? That's 15, that's 8. So let's put that time function call in there, time 0. Now I believe this will not compile because I need the header file to get that time function. It works. There it is. Look at the last digit of the last number. See, the last digit of the last number is different every time. So now that's working. But it'll only work if you wait a second between runs, right? So I did, let me just play with this, and I've never tried this before. What happens, how do you run more than one line at a time? I think you can do something like this. Does that run it twice? That runs it twice, doesn't it? And look, it gives me the same sequence twice. This lets, that semicolon lets me run two commands, one after another on the same command line entry. This is the first 5 numbers, and it's the same as the second 5 numbers. That's because the seed, at time 0, returning the same number of seconds, because it ran so quickly. So you have to wait at least a second to get a different seed. Okay. And once again, I don't think that'll compile in the lab or on Windows, but I'm not sure. Let's see, if I put that header in there, is it going to complain? I don't think so. I get the same thing. I think you're going to need that header. All right, the last thing we need to do is change that to 100. And let's see, there's 100. Now, let's redirect from the standard output from the console to the file numbers.txt. See, it didn't display anything, but there's the file that was created. So that redirection operator works. Then we can look at numbers. I'll use VI for that. Oh, there's nothing in there. Oh, it's the compiler. Sorry. I ran the compiler and I sent the output to numbers, which is, there's nothing from the output. So we compiled it. Let's run a.out. There it is. There's the numbers, 100 numbers. All right. I think that's everything. And now there's any questions on that? So we covered loops, and mainly loops, really. Now here's another exercise. This is very tricky. And I threw this in there. This is not an easy problem. You know, this course is not, it's taught as, you know, an intro to computer science. It covers programming from, you know, the first point. But we recommend that you have a programming experience beforehand. Right? And so these problems are not, some of these problems are not trivial. Like this one here is, it digs into subtle issues that you may not have seen in your first exposure to programming. So this is not a simple problem. This is a hard problem. And it exposes some issues that a lot of people don't think about when they start coding. All right, here's the problem. Write a console program that converts meters into feet and inches. The program starts by asking the user for a measurement in meters. The program should accept a floating point number. After getting the number, the program computes the number of feet and inches equal to the specified number of meters. The program outputs feet and inches as whole numbers. The program should round the number of inches correctly. Test that your program produces the following outputs for the given inputs. So when we input, these are meters, so 0.3049 meters. And we put that into the program, it should display 1 foot 0 inches. That's the number of meters in a foot, approximately. If we input 1 meter, then we're going to get 3 feet 3 inches. That's some rounded value. they put in 2 meters. We don't get 6 feet 6 inches because there's rounding going on. We're going to get 6 feet 7 inches. So we're going to round up in that case. But those are the 3 test cases. So once again, we have to write a console program that reads a number of meters that the user types in. And based on that value that's typed in, it prints so many feet, so many inches. Now this is number 4, right? Number 4. And I'm going to copy problem 3 to problem 4. I don't think we need that. This is not a random number generation problem. We don't need that. We want to have a loop. Let's do I'll get rid of this too. Let's do it like this. Let's start really no. Let's declare a value which is meters. And then we'll prompt the user to type in the number of meters. You know what? This is called refactoring. I said, well, you know, I'm going to delay that declaration to there. I just decided to reorganize there. Let's go refactoring. You should think about that. Always be cleaning your code all the time. It's very hard to build out solutions to problems if you let your code get messy. They always have to be kept under control. And this is not a big deal, but it's just my preference. I thought, oh, I want to delay the declaration of meters. And then now we prompted the user to enter in the meters. And then we'll use cin with the input operator and read into the variable meters. I'm going to get rid of the uppercase M too, just like that. And then once I get that in there, I'm just going to turn around and I'm going to say, okay, I guess. Meters. 1. Just says okay. Actually, instead of saying okay, let's print the number of feet. And let's declare feet here. So I'm going to do integer feet equals. So how do I convert meters to feet? I can divide by meters per feet. How many meters per feet are there? 0.3, what's that in here? Is that right? 3049? Is that how many meters are in a foot? Oh, 3048. So let's see, if 3048, if I type in 3048 here, I divide by 3048, I should get 1. You know, there's a problem with this. This is a very tricky problem. And I think I haven't done it right in the past, to tell you the truth. I have not done this right in the past. And so I gave as a test case 3049. So 3049 divided by this will give us, it'll give us 1 because it rounds down. But if I type in 3048, it's probably going to give us 0. Because the this fraction probably cannot be exactly represented in computer memory. You know, like a third. Say the number 1/3. In math, you say a third. That's a very precise concept. 1/3 is a rational number. You know, it's a ratio of two integers. But in computer memory, there's no way to use normal representations that are used in RAM to represent 1/3 with as a single number. You can represent it as, you know, a 1 and a 3 in separate sort of storage locations. But you're going to get some approximation of a third. You know, when you try to represent a third using decimal notation, it's like 0.33333 as it goes to infinity. That's the same problem with the computer memory. You don't have enough bytes. You don't have enough bits to. It's a repeating decimal representation. So that's the problem that we're dealing with here. All right. So now look at this. This value here, if we made this a double, then we won't get an integer. Let's take a look at what it looks like if it's a double, okay? So 1 meter is 3.28084 feet. Oh, and a 0.3048. What if I did this? 0.3048. Did I do that right? So you get to 0. It should be a 1, right? That's because of that. It's like a round-off error. It's a truncation error. It's not actually rounding. It takes the 3048 and represents it as something else. And so it is an issue. So let's do this. We're going to do this. We're going to take just a small. Oh, we don't need that parenthesis. Let's just pull it up a tiny amount. You think that's going to give us a 1? I'm sort of guessing here. I don't want to get into this in too much detail. 3048. Oh my God, it still doesn't work. What's that? 1 times 10 to the minus 9? That's pretty close to 0, right? So what is going on here? So this thing here. Oh, meters is an integer.
Yeah, what if you make it double?
So this should be a floating value. .3048. Still not working. Am I doing this right?
What if you on the top?
Yeah.
Where you assign?
Oh, no, I'm sorry. Meters, I'm typing in meters should be a double.
Right there, yeah.
Yeah, thank you. I don't know what I was thinking. Meters should be a double. There we go. All right. And let's do this. I'm going to comment out that section there. I wasn't doing that right. See, meters is coming in as an int. So if I type in 0.3048, and when we read it in here, it's stored as a 0. So now we're going to read meters as a double. Thank you for that. 1. So it works without adding. So it seems to work without adding. If we put in a little nudge like that, we'll get the same amount. See, it's same one. And I'm going to take that out. It seems to be working without that. All right, I think that's good enough. So this is feet in as a double precision number. So let's go back here. I want to run that again. Yeah, see that's giving us a floating point number. Okay, now instead of a double, let's declare feet as an int. So now when we get a floating point value for this expression, we're going to try to cram it into an integer, which means the fractional component gets discarded. It doesn't get rounded; it gets discarded. So if it's 1.99 feet, it'll be stored as 1 feet, 1 foot. So the 0.99 will be discarded. It's not rounded. So this computer languages don't round automatically. They truncate, they chop. If you want to get rounding, you have to add 0.5 in this case. All right, so let's see what it does here. So it's 0.3048. Now, does this give me a 1? It does. And 1 meter gives me a 3. 2 meters gives me a 6. That's what we need here. 2 gives me 6 feet. 1 gives me 3. 0.3049 gives me 1. So far we've got the feet part figured out. Now we got to get the inches part figured out. Oh, sorry. Okay. How do we do the inches? Well, let me work on that here. So there we figured out the feet. Now the inches, let's declare the inches as a double. I've done the problem before, so I'm using my memory here. So although I've done every time I do it differently, but I know the general sort of gist of the problem here. So the inches, we'll declare that as a double, and think of it like this: we take the meters. Oh, wait a minute. We're going to take the feet. I'm going to change this around. How am I going to do this? This is, I'm going to declare this is a double. This is feet, which is meters divided by this. And then inches is going to be feet times 12. So these both represent the number of meters. One is given in feet, and the other one is given in inches. So 6.56 feet or 78.7 inches. That should be roughly the same thing. Right? 6 times 12 is like 72, so that's about right. So both of these values represent, this is the number of meters in feet units. This is the number of meters in inch units. So now what I'm going to do is this. The feet that we need to display, I'm going to call it FT. And that is the feet just truncated. So I'm just going to print this FT. Well, watch this. Yeah. Watch what I'm doing here. Get rid of that. So I want to start start this process here. This is ft feet. And inches. Oh, in is not a reserved word. So some languages, in is a reserved word. I don't think it is in C++. So it's, I'm going to have to put a space there. So we have, and I'm just going to declare in to be 0 for now. Okay, so we're going to get 0 inches. So I'm going to print ft, this is a variable, which is going to be an integer here. It'll be the truncated version of the floating point representation. And then it'll be followed by the text ft with spaces around it. Then it'll be followed by the integer value for the number of inches, which we need to figure out, followed by a space and then in. Let's see if that compiles. I think in is, my concern is a little bit here that I'm using in as a variable. You know, like you can't use a reserved word. Like I can't do this. Let me show you this. You know, a for loop. For is a reserved word. We can't declare a variable named for. Let's see what happens when we do. See, it's choking on for. So, well, I want to use in, but I know in some languages, like JavaScript, in is a reserved word. I can't declare a variable called in JavaScript. But I don't know about C++. I don't think it exists in C++. Oh, we got away with it. It's okay. So we run this thing. Meters 2, 6 feet. Meters 1, that's 3 feet. Okay, that's working. Now we just have to get the inches working. All right. This is the number of meters in feet. This is the number of meters in inches with fractional components. So here we get the feet from that foot value with truncation. And then the inches are going to look like this. It'll be these inches minus the number of inches that were taken out as feet. I don't know if you see that. So, you know, if it's 3 feet, then I'm going to take out 36 inches. So I want to take out 12 inches for each foot that I display as a foot number. So that's why I'm taking those out. And then I'm left with just the inches.
So that's how you get what's left over.
Huh?
That's how you get what's left over, is what you're saying. Whatever hasn't been used in groups of 12.
Yeah, that's what you have left over, exactly. So now, it's not quite there yet, but let's see what happens. The meters is 1. How does that look? Looks good, right? Is the next one going to be right? Well, I think it's going to be wrong. Anybody want to jump in there? See, it's a hard problem. So let's try 2. Yep. See, we're truncating. We need to round it. So this value here, this is a floating point value. Ft is an integer, 12 is an integer. See, this multiplication is performed first. It has higher precedence than subtraction. First we do the multiplication. We take an integer feet, multiply it by an integer 12, and we get an integer result. So we take a floating point number inches and subtract an integer value. And that results in a floating point value. So if you take a floating point value and you combine it with an integer value, it always results in a floating point value. So this expression evaluates to a floating point value. This expression on the inside evaluates to an integer value, because ft and 12 are both integers. But inches is a floating point, and this value is integer. So it doesn't matter what this is. We just have one floating point value. And then the result, starting at this left-hand parenthesis and ending at the right-hand parenthesis, that whole expression evaluates to a floating point value. Now, we take that floating point value and we try to jam it into an integer. That's where we get truncation. That's where the fractional component is discarded. This is where we have to do the rounding. So we do, and this is the trick. It's very simple to do rounding. We're going to get truncation. So we add 0.5. That's it. And then truncate. It gives us rounding. And by the way, we don't need this. We don't need that. We don't need that. We don't need that. Because it shows, explicitly the order of execution, but we can apply the rules of precedence to know the order of execution. Now we have less symbols to look at. Here we are. Is this going to work? It does. It worked. And for our final test, let's try 0.3049. There it is. That was hard, right? Not. It was hard for me. And that's it for today. All right.